In this video, we want to be able to distinguish energy stocks, which is how much energy you have, such as a gallon of gas, or some thermal energy stored in some molten salt. We want to distinguish that from the flow of energy, or power, which is the rate at which energy is transformed from one form to the other, such as sunlight hitting a photovoltaic panel. We're transforming radiant energy into electricity, or the rate at which an engine turns chemical potential energy of gasoline into heat and kinetic energy of the moving vehicle. We will learn that there are three primary sources of energy for the Earth, one big one and two small ones, and that energy is transformed often in many steps from one form to the other, and ultimately it's almost always radiated into space as heat.
The sun shines upon us, and the energy comes to us through radiant energy, okay, warming the Earth. And so this is where most of the energy for our activities comes from, but also there's two others that are very small, and that is the Earth is rotating, and so it has some kinetic energy. And we can actually harvest that in the forms of tides, because there's a certain bulge on this side and another bulge on this side, especially if the moon's over here, right? Your tides from the moon are bigger from the sun. And we can harvest the energy as we rotate through these bulges. And there's one other source of energy, and that is nuclear. So we have this, like uranium, for instance, inside of the Earth. And we can use it in two different ways. One is we mine it and we use it in reactors. But also, that's what makes the Earth hot on the inside. And that geothermal energy is actually a form of nuclear energy, because the Earth wouldn't remain hot if it weren't being heated from the inside. Okay, so we recognize all of this energy is coming into the Earth from the sun, mostly from the sun. And its energy must be changing if the energy was constantly coming in, but the energy is actually also going out at the same rate. And that is, the Earth is radiating infrared radiation out into space to keep a balance. So all of the energy that comes in from the sun is eventually radiated back out into space, and at the same rate, so that the change in temperature of the Earth stays constant. Now, we recognize that's not perfectly true with this climate change thing, that we're putting a little bit of a coat around the Earth with the carbon dioxide, and so therefore we've reduced this infrared radiation because it absorbs it, kind of like putting a down coat on the Earth. And so what's happening is the temperature of the Earth is, yes, going up just a little bit, because slightly more energy is coming in from the sun than going out. And when the temperature goes up, we'll radiate more, bringing us back into equilibrium, but at a higher temperature. This describes all the energy flows in the Earth, or to the Earth. An energy flow is an arrow. Okay, so we show these arrows, and an energy stock is a circle, okay, where we store energy on the Earth. All of the power use, the rate of energy use of the human race is 15 terawatts, or 15 trillion watts, right? But this is a little bit old, so now it's probably about 18 terawatts. And you ask yourself, do we have that much energy coming in from the sun? And we recognize huge amounts. Okay, we have 162,000 terawatts. So the ability of us to obtain our energy, theoretically, from the sun should be very easy. There are two other sources of energy, and one is nuclear. Okay, part of it is the nuclear energy that we have inside the Earth, such as uranium that we can use. But also, it's this decay of radioactive material inside the Earth that provides the thermal energy to drive geothermal processes. Okay, and the last source of energy is the kinetic energy, because the Earth is turning. And how can we harvest that? Well, we have these tides that stick out on either side from the sun and the moon of the Earth, and we can harvest that energy. And you can see we harvest a tiny amount of energy from tides. In fact, these tidal energies are very small, 3.7 terawatts, the rate at which this power is dissipated, compared to the 162,000 terawatts from the sun. And the geothermal energy, again, is very small. And we can see that our nuclear fuel provides us with 1 terawatt. Okay, so on the order of 1/18th of all the energy that we consume as humans. But we recognize it'd be reasonable to say that the sun provides us with essentially all of our energy needs, whether it be directly heating the surface, or through photosynthesis. 90 terawatts is converted to plant matter. And so here, this is all of the energy that's presently exists as plants. But old plants constitute coal, right? Deep in the earth, lots of energy, oil, and natural gas. And this is the rate at which we use that energy. So this is our power, or our rate of energy use. 3.6 terawatts are being dissipated on average all the time from coal, 5 from oil, and 3.2 from natural gas. And so we can expand our energy flow that we just talked about with Pete picking up the rock. What did we have? Well, the rock had potential energy, right? And it turned to kinetic energy through the virtue of the force of gravity, right? Also, the rock was lifted up from the ground by virtue of the work of Pete. But where did that energy come from? Oh, that came from Pete's huge muscles, which the energy actually, so the power came from the muscles, but they were just converting, this energy, this chemical potential energy in Pete's body, this ATP, into the potential energy of picking up the rock. Well, where did the potential energy from the ATP come from? Well, that was from the chemical potential energy in Pete's food, the glucose. The food turned to glucose, turned to ATP. So where did that food get its energy? It could have been beef, right, who ate plants, but ultimately it came from plants, and that came from the radiant energy of the sun. Now you could say, yes, the sun has nuclear energy through fusion, but it's enough for us to say we're getting radiant energy from the sun. And it turns to plants, which I eat, make that ATP molecules, which drive my molecular motors, and that work gave potential energy to the rock as I picked it up. The force of gravity pulled it down and gave it kinetic energy. It hit the ground. This kinetic energy turned to heat, which we symbolize as Q, through the force of friction as it hit the ground. And that Q ultimately radiates out into space, into heat in the space. So this would be like radiant energy, IR, into space. So it comes from space, from the sun, it radiates back into space. Now, I don't mean to say all of the energy from the sun goes to the food, goes to the ATP, lifts this thing up. We recognize along the way, a lot of the sun's heat does not go to food. It just goes to heat up the earth, and that radiates out. As well, not all of my food went into ATP. Not all of the ATP went into work. So these processes are not 100% efficient. A lot of energy, is we could say lost to heat, which ultimately radiates out. But we can define the energy processes that are central to this rock as radiant energy turning into chemical potential energy, the work providing potential energy, gravitational potential energy on the cliff, to kinetic energy, to heat, and then radiated back into space.